there's a long fancy derivation of it, but that's sort of what I was doing over here. This is sort of the backwards derivation, pseudo derivation. So,
And is that actual notation, or did you just make that up? The sigma with the circle in it?
properly. Integral with a circle, which is proper notation.
Okay.
Dot EL.
Because I'm doing this in calculus right now, I just didn't know if you can add a circle in.
I've actually not seen it, but it makes sense that why not?
Can you also do other shapes, or is it just circles?
Like a triangle.
Well,
Put a triangle.
you're trying to indicate that it's for length, it's some loop that ends back where it started.
Mm-hmm.
So circle is traditional, but I guess there's no reason why it has to be a circle, I guess, except for if you don't do a circle and your mathematicians are looking at it, they're gonna go, what the hell is this? Or what the heck is this? I don't know how math people speak.
And you said this is just missing one equation?
One equation and part of one equation. Now, these are Ampere's law. Anybody with a decent French accent? Not quite the E with the accent mark like that. I think it's a accent grave. Okay. Ampere, how it's pronounced. Ampere's law. This is Gauss's law of electricity. And Gauss's law of magnetism.
So all of Maxwell's equations are not his.
There will eventually be something added onto here, which is Maxwell's contribution. And then there's another one which Maxwell uses. Maxwell did not call them Maxwell's equations, that came later. It's what Maxwell does with them that was revolutionary. But that, we really need that last equation first before we get into that too much detail. Any questions before I jump back to what we were doing? All right, so I know that the force on current 1 is, we have the length times the magnetic field. Now, as long as the length and the magnetic field are perpendicular to each other, I can sort of drop the vector bit. Because with the cross product, if they're perpendicular, then we get the maximum amount. And I know that if I have another current, if I have another current here, I2 and I1, this magnetic field is going to be hitting at a right angle to the wire. So, excuse me, ILB, so that's I1, so this is a force on 1 from 2. I1 times the length that they're parallel, times B, well the magnetic field coming from the other one is mu naught I over 2 pi r, this will be I2. And what you end up with is mu naught I1, I2, L over 2 pi r, which is the equation that I started with. If the wires are not perpendicular to each other, you got to do a cross product.
What is the subscript on that first guy?
That's subscript B for magnetic, and then 1, 2 for, this is the force on 1
Oh,
from
1, 2. I thought it was a dash.
Oh, no, that's a 1. We had a serif. They're so much clearer. Now it's perfect. Just like each of you. Oh, I actually had numbers over there. Let's actually do that one again. So I had 3 amperes and 4 amperes. 5. Plug and chug, that's 4 pi times 10 to the negative 7 times 3 amperes, this is Tesla meters per ampere, times 5 amperes, times the length. Did I actually give a length? Let's make it, what number have I not used yet? Let's make it 10 meters. Divided by 2 pi times the distance between them. R is the distance between them, so this would be R here. And why don't we make this 2 centimeters? 0.02. So what is the force?
First, do you have to change the centimeters to meters? Or did you say meters? Oh, I thought you said centimeters.
That's centimeters right there, but I converted to meters so that things cancel out nicely.
Is that 4 pi times 10 to the negative 7?
Wait, 4 pi times 10 to the negative 7th, yes. I feel like I'm off on something here. Oh, not necessarily, okay.
I got 4.775 times 10 to the negative fourth.
Negative 4th?
Yeah.
Units?
Yeah.
That's
Tesla.
amperes?
What do we
Tesla.
find?
Newtons.
Oh, yeah. Oh. If you had not converted this into meters, then you would not have newtons there.
Now, because this might just work because we're finding the force. Because the Teslas aren't divided away by anything, are Teslas equal to newtons somehow?
Well, why don't we take a look at the equation over here? Let's find out if I made a mistake on the units. I know F is equal to QVB in terms of units. So a Newton would be equal to a Coulomb, meter per second Tesla. A Coulomb per second is, so a Newton is an ampere meter Tesla. So a Tesla is a Newton per ampere meter. So over here, if we did the more direct, I can't think of what units are, so let me sort of work it out. I'd have amperes cancels out with amperes, meters cancels out with meters. I'm left with Tesla times meters times amperes, which is
Also known as 18.
sure. Or an abbreviation of amount.
That's going to be what would you like to coverage?
All right, let me give you another equation. See if you can discern what it is. Let's just do the magnitude.
So the R is just the distance between the two fields, or two currents.
Do we have two currents in this problem?
No.
Okay.
It's the diameter.
R is the diameter.
The 2R is the diameter.
Oh, okay.
So
So
essentially,
it's just one magnetic field.
Yes, all right, because we got one current. All right, so we've established one current. R is the distance between what and what?
One. one end of, well, north and south, maybe? Like one side of the magnetic field to the other.
No. Trying to see how I can make that work, but I don't think I can.
Is it the distance between the edge of the magnetic field and the current?
When you say edge of the magnetic field, what do you mean?
Or we gotta answer that.
It is the distance from the current or the wire, and what?
So the loopy lines only go out but so far. So
As in, however, the magnetic field lines go on forever.
never mind.
Well, now, if you want to say that there is a limit, then the signal that's being sent out that for the magnetic field lines are can only move at the speed of light at the most. So if when the magnet's created, time times the speed of light tells you actually how far out they go,
Well,
which we will consider to be yeah, for now.
But
so you said it's the end of the magnet.
to the other end of the magnet?
Isn't that what you tried before?
No, I think I did something similar to in the
Oh.
end of the magnet.
When you're finding the electric field, there's an R in that equation. What is that R?
The distance between the hold on. Oh, the distance between it and the charge,
What is it?
the electric field, the charge.
The charge is right there at the electric field, and then it goes on forever. So what's R?
Whatever point you wanna find.
Yes. So what is this R?
Whatever I want.
It's the distance from the wire, which is carrying that current, or from the current, to whatever point you have in mind. Now, the reason I bring this up, especially this equation, is that if I have a long line of wire, a straight line of wire, then that magnetic field is mu sub naught over 2 pi r. Here I don't have a pi in it. This is the magnetic field. If I have a loop of wire like this, with a current running around in a loop like that, this is the magnetic field in the center of that circle, where that is R. Biggest mistake I see students make on this is that I give them the straight wire or the loop of wire and they get the equations reversed because they see 2 pi r and they think, oh, circle. And they think that's the geometry of the wire. It's not. 2 pi r is the geometry of the magnetic field. Here, 2r, pi's gone. It's the geometry of the magnetic field. It is not there doesn't look like there's a circle here, but it's the wire that is a circle. As a matter of fact, this basically is how magnets are produced. You have an atom, we've got a bunch of protons, N protons, and some neutrons. Not Q. Z neutrons, and I have electrons zipping around. If the electrons in a material are all basically zipping around in the same type of direction, because if I have a charge that is sort of going around in a circle, it is creating a magnetic field. I have a moving charge. And so if I have enough of them going in the same direction, the magnetic fields add. They are vectors, they add like vectors, and I get a magnet. If it's all completely random and each magnetic field cancels out with another one, it's not a magnetic field.
So, how do you take something that's not magnetic and make it magnetic?
All right, some materials you can, some materials you can't. So, aluminum for the most part is not a magnetic by itself, but I can put a magnet on it and it'll stick. And work. There we go. But that itself is not magnetic, because I can put something, if I put this up here, it's not like these are reoriented. So what you would do to create, a couple ways of doing a magnet. You can expose it if for materials that you can reorient basically the spin and the rotation, expose it to a very strong magnetic field. And that can basically bring it into alignment. You can also take a material and heat it up to a certain point where it's closer to a plasma or a liquid, expose it to a magnetic field at that point, and then cool it down, and the magnetic properties will remain.
Wait, so you can heat something up and give it a magnetic field?
Yeah.
Okay, I know what I'm doing this weekend.
Yeah, you probably don't have, hey, good luck to you.
Microwave and aluminum foil even.
Yeah, I would not recommend that one, but hey, you do you.
Blowtorch should get hot enough, right?
I don't know. But as you heat it up, you need to expose it to a magnetic field. It doesn't have to be as powerful as not heating it up.
So I have to heat the piece of metal up and have a magnet next to it.
Yeah. But don't heat up the magnet next to it.
So I have to heat it up without heating the other thing.
Yeah, that's something up. But how can you create a magnet? Suppose you want to create your own magnet. What would you do?
Grab Ebert, burn something.
Gravity.
You know, grab Ebert, have him make a magnet.
Ah,
I'm now a magnet.
slap it enough times to heat it up. Electromagnets, any of you played with this as a kid? Science project? Got one. Okay. Let's talk about the solenoid.
The what?
Solenoid.
Okay then.
If I take a loop of wire, I know the magnetic field in the middle is mu naught I over 2R. It requires calculus to derive it, so trust me. If I take a second loop of coil, well, then my magnetic field in the middle is roughly 2 times that. Each coil is producing its own magnetic field. So if I take a whole bunch of coils, as I add the coils again and again and again, I get more of a magnetic field in the middle. Now, very crudely, if I have N coils, the magnetic field in the middle is N mu naught I over 2R. In reality, it doesn't work out quite as nicely as that, but that is good enough for 152.
Why does it not work out?
Because the formula I gave you was in the middle of that coil, but if I have a solenoid that's this long, so I got a bunch of coils like this, that equation right there assumes that the magnetic field at this point from this coil still works by that formula, but I'm getting farther away from it.
Oh, so like in a lab?
Yeah.
Is that
Because basically you have one magnetic field at the very beginning of the coil and just multiplying it by 2, 3, 4, 5, 6, 7.
Yeah. Yeah. So if I've got a bunch of coils, and again, crudely, for those who missed my explanation there, that given these coils right here, this assumes that at any point in here, the center of any point in here, that the contribution from each coil is the same. And that the farther I am away from this coil, the less impact this has. Now, how do you know it's a solenoid as opposed to just a loop of wires? Well, sometimes it's both. But if I have a length here, and I have a diameter here, if the length is significantly larger than the diameter, solenoid approximation is good enough.
Are there different equations for both?
Say it again?
Are there different equations for a solenoid and just a loops of wire?
Yeah. We'll get there.
You should assume solenoid.
I want to check something first to make sure I didn't misstate something. Hold on. Oh, I apologize. I misspoke. I thought something was seeming off, and this goes to sort of what Jack was asking, and there was another question in there which I tuned out, so sorry about that. I'll have to ask again. I think you were asking something. This is not the magnetic field at the center of a solenoid. This is the magnetic field at the center of a small bunch of loops. So it's back. So that is, we're gonna derive a different formula for the magnetic field at the center of the solenoid. So, sorry about that. This is if I have few number of loops, so few loops. In small. Now, if editing were easier, I would just cut out that part that I messed up on. So what is the magnetic field at the center of the solenoid? All right, before we do that, were you asking a question that I ignored? Anybody else asking a question that I ignored?
Well, in your brilliance, you most likely answered it in another way.
Telepathy. All right, so if I get my loop of